All right. So now that we've learned about wave propagation, we can now talk about the decibel.
Oh boy.
So, what are we talking about when we say decibel? Well, here's the interesting thing. So, we talked about this a little bit because we talked about the amplitude of a sound wave, right, and how the amplitude tends to correspond to loudness. Okay. Well, here's the thing about loudness. If you compare a sound wave, a sound in the air, is accomplished by manipulating the pressure that you apply to the air molecules, right? So if you compare the pressure, the air pressure values for the quietest thing that we can perceive compared to the loudest thing our ears can tolerate, that is a difference of 1 trillion. So the loudest thing our ears can tolerate is 1 trillion times more pressure than the quietest thing that we can perceive. And 1 trillion is a really big number. And sound people don't like big numbers like that, generally speaking. We tend to go out of our way to not have to deal with numbers that big, as you will see. So part of, I can make this a little bit bigger. There we go. So part of like what the decibel is trying to do is the decibel is a way that we can measure that difference, that huge difference in perceived loudness, in a way that doesn't require us to look at a number with as many digits as 1 trillion. Okay. We would like to get that down to 3 digits or less, because we don't like numbers that have more than 3 digits, generally speaking, in sound. We go out of our way to avoid numbers that have more than 3 digits.
Why?
I don't know. We just do. Which leads to all kinds of jokes, like, when you're doing a sound check, why is it just always check 1 2 1 2? Because you lift on 3, right? Sound designers are afraid of big numbers like that. So anyway, we go out of our way to avoid this. So we have, in sound, we have we are so averse to that huge number of 1 trillion that we decided to create an entirely new unit of measurement that is derived using logarithms in order to avoid having to look at a number that has more than 3 digits. We are a very special kind of lazy. Okay? Right? So that's what we're talking about, is the decibel is this unit of measurement that we have invented that you derive doing actually complicated math in order to not have to look at big numbers. Okay? So that's what this is. So let's start talking about it. So decibel, what do we mean when we say decibel? Well, we can look at the root of this word. So a bell is where we started. And a bell is the result of a logarithm of, now this is for power, because we've figured out decibels for lots of different things, but for now we're going to talk about decibels as they relate to power. And power is most often encountered in terms of like power amplifiers that we use to drive loudspeakers with. That's where we find power the most. But as you'll see, power is not the only thing we care about. But when we're talking about power, a bell is the result of a logarithm of one power divided by a different power. And what that gives us is, it gives us a difference. Right? Because we're just comparing two values, two power values there, dividing one by the other, and then we're taking a base, it's a base 10 logarithm of this, and it spits out a number that's small. And that's because that's what logarithms do. And they spit out numbers that are small. And so we get a small number that represents the difference between those two power levels. So that the actual difference could very well be a really big number, but when you look at it as a bell, it's a small number. But it turns out a bell, because of the huge ranges we're working with, a bell is not enough to collapse this into a small enough number for us. So a decibel is a bell times 10. And so a bell times 10 gets you a decibel, and that usually gives us a small enough number that works for us. And before we get into like how do you actually do that math, turns out you don't always really have to do the math, because the way that the decibels work when you're talking about power decibels is you can kind of like fudge it in your head pretty easily, actually. So, and it's what I call the 3 and 10 rule. So if you multiply a power by 10, that represents a 10 decibel increase. If you double a power, it represents a 3 decibel increase. The opposite is also true. Like, so if you divide a power by 10, that is a 10 decibel decrease. If you divide a power by 2, that is a 3 decibel increase. And you can see over here on the right how this ultimately serves to collapse a large range of values into a smaller range of values. So, if we assume that 1 watt is our starting point, like that's our 0 just meaning there's no change, we're just like starting there, we're not comparing that against anything. 1 watt is our 0 in terms of decibels. Well, if we take 1 watt and multiply it by 10, we go to 10 watts. Well, that's a 10 decibel increase, yeah? So we would describe that as 10 decibels louder than 1 watt. Well, if we take that 10 watts and we multiply it by 10 again, we can now have 100 watts. But that's only a 10 decibel increase. So even though we're now 100 watts more than where we started, we've only gone up 20 decibels. Yeah? So instead of having to look at a 3-digit number, we're looking at a 2-digit number of 20 that represents that difference, the difference between 1 watt and 100 watts. Okay? Now, we'll multiply by 10 again. We get 1,000, but that's still only a 10 dB increase. So now we're up to 30 decibels. That is representing the difference between 1 watt and 1,000 watts. So now we're up to a 4-digit number, and we're representing the difference between that number and our origin using only 2 digits. Okay? We could multiply it by 10 again, and we get 10,000. Another 10 decibel increase, and now we're at 40 decibels. And so we've got a 5-digit number now in terms of power level, and we're representing the difference between that and 1 watt as only 40, which is a 2-digit number, really good. But here's where it gets really interesting. So to go from 1 watt to 10,000 watts is a 40 decibel increase. Another 10,000 watts, though, that's only a doubling, and so that's only a 3 dB increase. So going from 1 watt to 10,000 watts is 40 decibels. But doing 10,000 again, only 3 dB. So now we're at 43 decibels going from 10,000 to 20,000. How do we feel about that? You with me? See how this works? So we've now got a range of between 1 and 20,000. And we are representing that difference in a range of 0 to 43. And those are much easier numbers to do math on.
You might have answered this already, but why are we using watts?
Because I'm talking about power right now.
Okay.
And watts is how we measure power levels. Watts is, power is work. How much work got done? And we measure that in watts. So I'm just talking about power now, so we're talking about watts. There's no other reason than that. Other questions? Okay. Well, let's see what's next. All right. So here is just an example of that a power level between 1 and 10, and how does this look in 1 decibel increments? So you can kind of see, if you just like look at this a little bit, and look for that 3 and 10 rule that I was telling you about. So, you know, going from 1 watt to 2 watts, that's a doubling, so that's where we get 3 dB, right? We go from 1 watt to 10 watts, that's a factor of 10, so we get a 10 dB increase. See how that works? Okay, now, let's talk about how we can use this to actually figure out things without a calculator. So what power level is represented, you know, what decibel power level is represented by 80 watts? Well, going from 1 watt to 8 watts is 9 dB, right? And that's 8 watts. Well, if we multiply that by 10, that gets us to 80, right? And going from a factor of 10 gives us a plus 10 dB. So going from 8 to 80 watts is another 10 dB, which will be 19 dB. So 80 watts could be represented by 19 decibels. Yeah? Make sense?
Wait, before you remember this one. So you just added the 10 to the 9?
Mm-hmm. Because going from 1 to 8 was a 9 dB increase. And then going from 8 to 80 is a 10 dB increase for a total of 19 dB. Yeah? Okay, let's go the other way. What power level is represented by 1 milliwatt? Okay, well, a milliwatt would be how many watts? Yeah, 0.001 watts. Yeah? So that's what we're looking for, 0.001 watts. Okay, well, we know 1 watt, right? 1 watt equals 0. We could go to 0.1 watts, and that's dividing it by 10, right? So we would lose 10 decibels, right? Because dividing by 10, dividing 10 by 10, you get down to 1, you've dropped 10 dB. So this would be minus 10 dB. We divide it by 10 again, we get 0.01. That's another 10 dB, so now we're at minus 20 dB. We divide it by 10 again, now we're at the 0.001. That's another 10 dB decrease, so now we're at minus 30 dB. So we could represent the difference between 1 watt and 1 milliwatt as, well, that's a 30 dB difference. Or 1 milliwatt is 30 decibels less than 1 watt. Yeah? What about 4 milliwatts? Well, we know that 0.001, so 1 milliwatt equals minus 30 dB, right? Well, getting to 4 milliwatts, that would be 0.004, right? Well, 0.002 would be a doubling, so we would go up 3 dB. So now we'd be at minus 27 dB, right? Double it again, and now we're at the 0.004. We go up 3 dB again, and now we're at minus 24 dB. There you go. Yeah? Everybody okay? All right. So now, hopefully none of you wrote down those watt values.
I was just about to.
If you did, pretend like you didn't. because now we are going to figure them out in our heads using the 3 and 10 rule. You ready? So we're going to start with 1 watt. We're going to say 1 is our reference level. 1 watt equals 0 dB. So that should be everything we need to know to fill out the rest of this chart using the 3 and 10 rule. Anybody want to take a crack at one of these values, given what you've learned so far? Yes.
10 is 10.
Yep, okay. So multiply that 1 watt by 10, we'll get a 10 dB increase. So there you go. That one's easy.
2 is 3.
So 2 watts would be 3 dB increase, right?
Yeah.
Because is that what you mean? So, all right, yep. So we could put 2 watts there, and that would represent the 3 dB increase.
4 would be 6 dB,
Yep, so 4 watts, we double it again.
and 8 would be 9.
Yep, double it again, and you get 9 dB. There you go. All right, those were the easy ones. The rest of them are a little trickier.
I know what the next one is, but only because I remember what was on the last slide.
Yeah, but why? Why is the point?
Oh, yes. I'm trying to think how that.
I'm going to have a couple M&Ms while you're working on this.
Yeah, I know the next one is 1.25 to 1 level in D. No?
But how do you,
Well, I was about to explain.
okay.
Why? I'm thinking it's the 3 dB rule. Because,
So how do you get to 1.25 from one of the numbers you already have?
from one of the ones I'm not.
Yeah, that's how you got to do this.
Yeah.
So how do you use the numbers we already have to get you to 1.25? You want a hint? Are we ready for hints? What can you do with that 10?
You have it?
Ah, what would happen if we divided 10 by 2? That gives us a 5, and that would be a what decibel difference? A 3 decibel difference. So where would 5 go? Yeah. Okay. Now what?
We have it again.
I don't see why not.
That's the point.
5 for 4.
Yeah.
And then you could have that again to get 1.25 for 1.
Yep.
Can you add or multiply 1.25 to get 1.5 for 2? No, because the next one is supposed to be 1.6.
Would you have it, would you multiply it by half of 10 to go up?
That's what we did. That's how we got 5.
But I mean for the 8 dB level.
Do what with it now?
Like, would you times it then by 2?
8 times 2?
Mm-hmm.
That would be 16, which would give us a 3 dB increase. So that would be 12 dB. Does that get us anywhere?
Not here, but we can use that, can't we?
If you want to know how
I don't know. Can you?
Because I mean, if you have it, we'll just go to 8.
Yeah.
But can we do that with the 1.25 times it by 10 to get 12.5?
Oh, interesting. Look at that.
And then you have that. So it's
So if we go off the chart and we go to 12.5 watts, that would be how many dB?
6.25 or 11.
11 dB, right? Okay.
Because you just add 10 to the 1.
And now what could we do?
You could have the 12.25 to get
Mm.
6.25.
So 12.5 divided by 2 would be 6.25. That would be a 3 dB decrease, right?
Yeah.
And there's your 8.
Wow.
And then divide that by 2, and that's 3.12.
3.25. Wait.
And that's your 5.
125.
3.12.
Yeah.
And then if you have that again, you get the 2.
No, you get, oh yeah, which is 1.6.
Cool.
Mm-hmm.
Going off the chart to go back down.
There you go. See how that works?
Was there a way to find all the numbers without going off the chart? You had to
It
go
was
off
a
the chart?
trick.
Not using the 3 and 10 rule.
You challenged us, I think, outside.
There you go.
It's like I'm a teacher. Okay. Everybody get that? Okay. So let's do some of this with a calculator now. So if I say how much louder is 700 watts than 63 watts, anybody remember what the mathematical equation is to get you a decibel?
10 log, and then P1 over P0.
10 times the log of power 1 divided by power 0. So power 1 would be 700 divided by 63. Okay? So let's get calculator out and we'll do it. So if you're using pCalc, here's the order of operations. You do 700 divided by 63 and you get 11.111 repeating. And then I do the base 10 logarithm, so the log 10. And then I do times 10. And I got 10.46 dB. So 700 watts is 10.46 dB louder than 63 watts. Okay? That make sense? Everybody see how I did that? Okay. Here's another one. How much louder is 10,000 watts than 3,000 watts? Well, this would be 10 times the log of 10,000 divided by 3,000. So do this with me. Get your calculator out. So 10,000 divided by 3,000. Log 10 times 10. I got 5.23. Anybody else get that? Charlie got that? Ben got that?
I have the same number, but it shifted 1 decimal place to the left. I'm not sure what I've done wrong.
Probably forgot the times 10.
Oh, okay. Yeah, I see. That makes sense. Okay, yeah.
I got the correct answer last time, following all the steps, but this time I did my numbers very far off. Oh, maybe it's just not showing. No. That's the number that I got. which is very far off from your.
Yeah, that's not right. You forgot. Oh, yeah. You got to do 10,000 divided by 3,000. And then do the base 10 logarithm of that.
I thought I did do that. Oh, I forgot to press enter and then.
Yeah.
Yeah. Okay.
I usually don't.
Okay?
Okay. Yeah.
We wouldn't have
You got it now?
that's me.
All right. Okay, real deal question here now.
What were the other?
You are, well, I just mean, let's take this into reality now. Something that might actually mean something to you. So you're going to buy an amplifier. And you're at the amplifier store. You're at Guitar Center or whatever. And they've got amplifiers. And they've got a 350 watt amplifier and they've got an 800 watt amplifier. You have enough money for the 350 watt, but you really wanted the 800 watt. Like you went there to buy the 800 watt, but you're realizing I can't afford it, but I can't afford this 350 watt amplifier. Well, okay, if you buy that 350 watt amplifier, how much quieter is that amp going to be compared to the one you wanted? Like, what are you really giving up if you go with the smaller amplifier? Wouldn't that be a nice thing to know, right? Before you get all bummed out. Okay. So how much volume are we going to sacrifice? Well, let's do the math. 10 times the log of. Now in this case, I'm going to do 350 divided by 800. Because I would like a negative number out of this. I want to know how much I'm losing. Okay, and so I'm going to put the smaller number on top. Okay?
Is that just like a personal thing, or are you gonna like?
Yeah, because this is the way I'm thinking about it. Like, what am I giving up
Oh,
by going with the smaller amplifier?
so it's just the same thing, it would just be negative or positive.
Yeah,
Okay.
it's just, am I going to get a negative number or a positive number?
Gotcha.
I want a negative number here because I just want to look at it in terms of like, what am I losing,
Okay.
right? That's just how I want to look at it. Okay. What am I losing?
Very pessimistic approach.
Yeah.
How much is my cup empty?
Yeah, 350. 300, well, it is because like I went to the amplifier store to buy an 800 watt amplifier, and I don't got enough money, and so like I'm bummed out.
As we speak.
So great. What am I losing here if I can't buy the one I wanted, right? So it is. I am bummed out. Like this is a pessimistic view. Okay, so 350 divided by 800, log 10 times 20, or sorry, times 10, negative 3.59 dB. Okay, so I am giving up 3.5 dB.
Devastating.
What is 3.5 dB? What does that sound like? I don't know. Let's see. I'll just pull up Logic here and we'll play.
Times 10 or times 50?
350 divided by 800,
Yeah.
base 10 logarithm of that,
Yeah.
times 10. Okay. Okay, let me just go get something from here. Let's do this. Wonder if I can just put it out the big speakers. Oh yeah, there we go.
Ooh. You know they sell those at the gate.
Okay, so I'm buying a bass amp.
Nice.
So this would have been the 800 watt amplifier. This is the other one.
Pretty nice.
This is so sound. It's not too bad.
Okay.
I mean, it's noticeable
Can
that
you
I'm-
notice it? Yes. Right. Yes,
We're
you
also
can.
listening for it.
Yeah, you can notice it. But close your eyes now.
This is so sound.
Okay, you heard it change. But like, how big of a change is this?
Like I would notice it on sound gym.
Yeah. Like if you
If
didn't,
you're not a sound person, you wouldn't notice it probably.
Yeah. So it turns out.
And I had hearing
Okay, well,
aids.
no one hears the bass anyway.
So it turns out 3 dB is generally thought to be the smallest difference that an average person could notice. Like somebody who doesn't have training,
Sound gym.
yeah, who hasn't done a lot of sound gym or whatever, like, they could notice a 3 dB difference, but they couldn't notice a 2 dB difference. Right? So 3 dB is thought to be like that's the smallest difference in decibel difference that an average person would notice. Now, with training, you can get to where you can recognize a 1 dB difference. A half dB difference, very few people can. I mean, even I struggle with that.
I was about to ask.
Right? It's
I
like,
think the guy that can hear
Yeah,
polarity.
it's like
His name is David E. Smith.
It's like-
No, I like
honestly, like that. Whenever Sound Gym is giving me a 0.5 dB difference, is like it's a coin toss whether I'm going to hear it or not. So the question here is like, how bummed should I be about this 350 watt amplifier?
What's the price?
Not that much.
Yeah. No, that is
Yeah.
the question.
Yeah.
That's the right answer.
That is the right answer, right? So like, let's say
1 million.
it's $100 difference.
I don't
Not
care.
worth it.
Bro, what are your
How much
like,
is the cheaper one?
do you have a
though?
paycheck?
What's your paycheck looking like?
Yeah.
Well, that's what I mean. Like, you're short $100.
I mean,
Right.
if you pay like $500 for the cheaper amp,
Yeah.
you save some $100. But
Yeah.
also, if it's like 100 to 200, then yeah, buy the cheaper one if that's a big difference for you.
Yeah, I mean, of course, the answer is it depends, but
If you're covering your outlets in gold, I feel like it's
yeah.
You're going more.
But the point is, like, this is not actually that big of a difference in sound level, right? 3.5 dB is barely a noticeable difference. And so, yes, all other things considered, if there's no way you're ever going to be able to afford that 800 watt amplifier and you're going to have to live the rest of your life with this 350 watt amplifier, like, this is not going to be the most depressing thing about my life, right? Like, I really haven't given up that much. Okay? So, all right. There's an example of how understanding how decibels work can help you wrap your head around a scenario, right, of what this actually means. Okay. What if you want to go the other direction? What if you have the decibel difference and you want to figure out what difference in power that represents? Because so far we've just been given the power levels and we want to know what is the decibel difference. What if we want to do it backwards? Well, you figure this out using what's called a power ratio. And you figure out a power ratio by you do 10 to the power of the decibel difference divided by 10. And then you multiply that by the power that you started with. So let me demonstrate. So what is the power ratio of a level difference of 13 dB? Well, that would be 10 to the power of 13 divided by 10. So using my calculator, I would first do 13 divided by 10. I get 1.3. And then I'm going to click this 10 to the power of x button. And that'll put the 1.3 where x is. And I get 19.95. Anybody else get that? Is that what you got? Okay. So what is this number? Well, 19.95 is a magic number. If you multiply any power level by 19.95, you will get a power that is 13 dB more.
Why 13 specifically?
Because the 19.95 is the power ratio of 13 dB.
Nice.
Oh.
So is it like
So
that
it's
for
kind
all
of like
power
the
ratio?
chart,
Mhm.
but for the number 13.
Yeah.
So you can do that with any number.
Exactly.
That's simple. Okay.
So I multiply any power level by 19.95, and I will get a power level that is 13 dB more. Okay. So let's look at how this plays out in real life. So you start with 300 watts, and you want 13 dB more sound. So you've got a 300 watt amplifier, and it's not loud enough. And you say, I need 13 more dB. And you got to go back to the amplifier store and buy a different amplifier. What kind of amplifier are you looking for? Well, it would be the 300 watts that you have times 19.95. What is that? 300 times
985.786945 probably.
I just got 5,985 is what I got. 300 times 19.95? Okay, so I'm looking for basically a 6,000 watt amplifier. That's a pretty big amplifier, actually. That's going to be an expensive amplifier.
Just for 13 dB more.
Exactly. Yes. Yes. Okay, now I have to ask myself, do I really need that 13 dB?
Depends on what you're doing.
Yeah, maybe. I mean, a 6,000 watt amplifier, that's going to be pretty expensive.
Have you ever seen one before?
Sure.
Are they big?
We have a 10,000 watt power amplifier in our shop.
Rockville makes one for $400.
Oh,
Really?
get on that, Jason.
Again-
Blow up the shop as soon as
Yeah.
possible.
The correct answer is just plug a DI into the rest of the sound system and let all of their expensive equipment make it happen.
Okay, so there you go. So you at least have the answer. Now, whether that's reasonable or not, or whether you can get that or not, or whether you can afford that or not, that's another conversation. But I'm just saying, like, now you know what you're looking for. Okay? So that's how you would use that power ratio math. Okay, so let's try some more things. So we're going to have to make a couple of assumptions here that I just need you to, like, roll with me here because there's a few things I haven't explained yet. Okay, so just like there's a couple of things I just need you to take at face value. Okay, so you have this loudspeaker. Let's assume for the purposes of this exercise that we can also measure sound pressure with decibels. Okay, spoiler alert, you can, but I just haven't taught you how to do it yet. But let's assume that you can, and you have this loudspeaker and this flux capacitor that lets you measure sound pressure in decibels tells you that the loudspeaker is putting out 60 decibels worth of sound pressure. Okay, and you're only putting 2 watts of power into this loudspeaker.
That's crazy.
Okay, it's actually not that great. This is not a really efficient power output, SPL output for 2 watts. You should be able to get way more decibels than that out of 2 watts. But this is the scenario. You're getting 60 decibels worth of sound pressure with 2 watts. And you're like, yeah, that's not enough. I need 98. How much power do you have to put into that loudspeaker to get 98? This is the question. So the first thing I want to find out is what's the difference in decibels. So I'm going to do 98 minus the 60 I already know how to make. So what's that? 98 minus 60 is 38. So I'm looking at a 38 decibel difference. So now I want to know, well, what's the power ratio of 38 decibels? So this would be 10 to the power of 38 divided by 10.
You can't see Jason.
10 to the power of 38 divided by 10. That would give me the power ratio of 38 dB. So let's figure that out. 38 divided by 10, 10 to the x. I got 6,309.57. Is that what you guys got? Okay. So that is the power ratio for 38 decibels. And so I can multiply any power level by that number and I will get a power level that is 38 decibels more than that. So I'm going to take that 6,309.57 and I'm going to multiply it by the 2 watts I started with. So times 2, and I get 12,619.15 watts. Is that what you guys got? Yeah, this isn't going to happen, right?
12,000 watts.
Not going to happen. I need a better loudspeaker.
The generator.
What's determining how much output you get for your watt?
Good question. It's called the sensitivity, the loudspeaker's sensitivity. And if you look up, we'll do this in a little bit here, but you can look up a loudspeaker specifications and it will tell you what's called the 1 watt, 1 meter sensitivity. And it'll say, you put 1 watt of power in this thing and then measure it 1 meter away, you should measure this much decibels of sound pressure level. That's the sensitivity. And you can use that information to then figure everything else out, right?
We did last semester, right? The smart, the SPL.
We measured SPL, yes. We didn't measure sensitivity, though.
Okay, we're different things.
Can you measure sensitivity?
Yeah. Well, yeah. I mean, if you know how much power you're outputting into the loudspeaker, and then you measure the actual pressure in the air, then yes, you could figure it out. So if you knew those 2 things, then yeah. Okay, but usually you just let the manufacturer tell you because they figure it out for you. Okay. Okay. Oh, so how are we okay with power decibels? All right, let's talk about force now. So force decibels, force is like pressure, current, voltage, basically everything that's not power. Everything besides watts is a force. So pressure is a force, voltage is a force, current is a force. Anything that's a force, you can also do decibels, but the math works a little bit differently. So force follows a 6 and 20 rule. So you multiply a force by 2, you get a 6 decibel increase. You multiply a force by 10, and you get a 20 decibel increase. Yeah? And here's our chart, just like we had before. It's still ranging I'm just using volts in this case, but it could be any force value, ranging from 1 to 10 volts. Has a range of 0 to 20 decibels. Using all the same methodologies, right? Yeah, so far so good. So, we could do a little bit of this math again. What is the level difference between 2 volts and 10 volts? Well, 2 volts is 6 decibels, and 10 volts is 20 decibels, so it's 14 dB, right? 14 decibel difference. Just looking at the chart.
Wait, can you go back and do that again?
What is the level difference between 2 volts and 10 volts? Well, 2 volts is 6 dB.
Yes.
10 volts is 20 dB. 20 minus 6 is 14 decibels. Difference of 14. Yeah. Yeah, so 20 minus 6 equals 14. 14 dB. Yeah? What is the level difference between 1 volt and 100 volts? Well, going from 1 to 10 is 20 dB, and you multiply by 10 again to get to 100, that's another 20 dB. So 40. 40 decibel difference between 1 volt and 100 volts. Okay, so same deal. Let's build the chart in our head again. 1 volt equals 0 dB.
10 volts equals 20.
Yep. 10 volts equals 20.
2 volts equals 6.
Yep.
4 is 12.
So we're just doubling, right? Going from 1 volt to 2 volts, and that's a 6 dB difference. And then you double it again, you get another 6 dB. Yeah, double it again, you get to 8 volts, and that would be 18 dB, 6 dB amperes, okay? Yep, take 10 divided by 5, you drop 6 dB. So that would be 5 volts, would be 14 decibels. 2.5 would go there, right? And then 1.25 would go there.
You do the same thing of 12.5.
Yep, so we go off the chart, we go to 12.5, we multiply it by 10, and now we're at 22 dB. Yeah?
You have that for 6.25.
Yep, so we go have that, we get 6.25, drop 6 dB, and we're at 16.
3.1 or 3.125.
Yep. Have it again,
One more time.
and then have it again. 1.56. Yeah? So it's the same process, it's just a doubling gets you 6 dB, and multiplying by 10 gets you 20. Okay? So the bang for your buck is quite a bit better when you're dealing with forces than it is with power. So here's the equations, same deal. You don't need to write all of these down, it's all the same thing. I'm just showing you that the voltage, current, or pressure, those are the things we tend to look at. They're all forces. So any sort of force thing, you're trying to get the decibel difference, it's 20 times the log of one force divided by the other force. You want the ratio of that. Do you want to go the other way? You got the decibel difference. You want to actually get the real thing. 10 to the power of that decibel difference divided by 20 this time instead of divided by 10. And you get all the same things. Yeah? So if you're going to write anything down, just write down those two equations because those are the ones you're going to need. I am told by people who know these things that these are the variables typically used for voltage, current, and pressure. But I don't know who decides that, and I don't know why we have to care about that, but there are people who care, I guess. All right, so let's try it now. What is the dB difference between 2 volts and 63 volts? Well, that would be 20 times the log of 63 divided by 2. Right? So 63 divided by 2, log 10 times 20. I got 29.97 dB. Is that what you guys got?
Yes.
There you go. Let's try another one. This is just to show you that this isn't always about sound. We use decibels for all kinds of things besides sound. What's the dB difference between a 9-volt battery and a AA battery? Well, anybody know what the voltage of a AA battery is?
1.5.
Yeah, 1.5 volts. So
What, did I knew it, or it's 1.5?
That you knew.
it's written on every AA battery you've ever held in your hand in your life.
Yeah, just for fun. I just read all the text.
Yeah.
No, I did electronic stuff when my grandfather was okay.
Okay, so yeah, AA battery is 1.5 volts. So what's the difference? This will be 20 times the log of 9 divided by 1.5. 9 divided by 1.5. Log 10 times 20. I got 15.56 dB. I don't know why you'd ever need to know that, but
What do you do?
Just curious.
but the point here, the point of this question is that to understand that decibels just measure the difference between two things. That's all they do. Decibels do not give you any absolute values. They just give you relative values. I mean, you could compare the number of ferrets in one cage to the number of ferrets in another cage. And
Have you ever done that?
no,
Guys, field trip, Petco, right now.
right?
Do you think they have ferrets?
You should have to decide if ferrets are a power or a force.
What would you categorize?
I don't know enough about ferrets to know, but
Force. It's very
I
force.
would
Sounds
say-
cool.
yeah. Ken, you had a question?
I accidentally did 1.5 divided by 9. Would be the negative.
So you would have got a negative 15.5 then. Yeah. Mm-hmm. Okay. This is another one I just want you to take. I haven't taught you about reference levels yet, but there is such a thing as reference levels, which we'll talk about probably next time, unless we have time to do it today. But we'll see. See how if anyone's brain melts before 3 o'clock. But so take this at face value. There is such a thing as dBUs,
Which is?
decibels with a little U attached to them.
What is the
That's
U?
like-
I'll tell you later.
Is it like a unit?
It stands for unloaded.
And-
So
Never mind, sorry.
so professional line level is plus 4 dBU. Just believe me.
Okay.
I'm paying a lot of money to believe you.
If you want to be a sound person, you just have to believe that.
Who decided that?
I will explain later.
Okay.
There is a method to the madness here, but if 0 dBU equals 0.775 volts, then how many volts is professional line level? This is the question. All right, so I have a decibel difference. So I would like to find the force ratio of 4 dB. That's what I would like to know first. So I'm going to do 10 to the power of 4 divided by 20. So 4 divided by 20, 10 to the x, I get 1.58. Is that what you guys got? Yeah? Okay. So that's a magic number. I can multiply any voltage by 1.58, and I will get a voltage that is 4 dB more than that. Okay? So I have the voltage value for 0 dBU. So if I multiply this 0.775 volts by 1.58, I will get the amount of volts that equals plus 4 dBU. So 1.58 times 0.775, and I got 1.23 volts. And this is real. Professional line level actually is plus 4 dBU, and it actually is 1.23 volts by definition. And it's a joke.
Please explain.
Is it part of the sound joke? I can't count.
Yeah.
1, 2, 3.
1, 2, 3.
I don't get it.
Check. 1, 2, 3. Check. 1, 2, 3. There's an actual scientific reason. There's an actual scientific reason why 0 dBU is 0.775 volts, but there is an absolutely not scientific reason and only stupid funny reason that plus 4 dBU is professional line level.
Right.
So the professional number isn't that professional.
No, it's a joke.
You can see why they went into sound and not comedy.
But I look love when like professions have inside jokes.
Oh yeah.
Everybody.
All the time.
Bites and nibble.
Yeah.
Yeah,
We
like
talked
I-
about this.
I love.
So we've like, we've for the last 30 to 40 years, every sound manufacturer that's putting out professional sound equipment has designed the circuits to run at a nominal operating level of 1.23 volts.
It's too much time on their hands.
Can you random
Choose to be lazy
question,
about
but
other
it
things, though.
might sound silly.
Yes.
Remember those fake speakers that were at the place where Sam was seeing the jazz ensemble last year?
Oh,
Yeah,
the
like
counterfeit
yeah,
JBLs,
counterfeit
yes.
JBLs. So
Yes,
would you
yes.
call that unprofessional? No, but I'm being serious. Like unprofessional.
Professional has to do with it's generally speaking, it's the difference between balanced and unbalanced audio. Okay, so consumer levels is consumer level versus professional level. So consumer level stuff is the stuff you buy at Best Buy. Okay, and that's for living rooms and houses. Okay, yeah, and it's going to be running at what is called consumer line level, which is actually 0.316 volts. It's a lower voltage, mainly because it's not balanced. It's unbalanced audio. It doesn't have to travel very far. It's just only going from like this thing to that thing on the shelf. Professional stuff tends to have longer cable runs, and therefore, we balance those signals and run them at a little bit higher voltage. So that's the difference between consumer and professional. It's just like how is that signal built and then sent down a wire.
In the same way, I'm guessing that if it's like a professional, like if it's used for professional use, that you have to be careful if you're using it for your home.
Absolutely. So that's one of the little math problems we're gonna do later, is what happens if you try to interface a consumer line level piece of equipment with a professional line level piece of equipment. Like what happens? No, but turns out you just have a level difference. Okay. There's another way of looking at this. You can also look at force decibels in terms of pressure, like what happens in the air when you make sound. And so if you think about the pressure, you've got a thing that's making sound, like here in the center of this sphere. Okay, and it is applying pressure to the air molecules, right? We learned about this. Now that pressure radiates equally in all directions. And so if you now measure it at some point along that sphere of pressure radiation, you will measure some now amount of pressure, right? It will be less, though, because the pressure is being distributed across this sphere, right? So whatever you measure at the center is going to be more pressure than what you ultimately measure at a single point in space some distance away, because it's dissipated over a surface area, yeah? Well, if you then go out and measure it again twice as far away as the first time you measured it, now that same amount of pressure is being dispersed around a larger sphere, and so the pressure you would sample at a given point in space at this distance will be less again. And it turns out that it follows the 6 and 20 rule. So every time you double the distance away from the sound source and measure at a point in space what the actual pressure is, that pressure will drop by 6 dB. Every time you double the distance away. And if you think about it, that makes a certain amount of sense, given what we've learned so far about how force decibels work, because pressure is a force. So it's called the inverse square law. So every time you double the distance away from a sound, it will get 6 dB quieter. If you multiply the distance by 10, it's 20 dB quieter. So you go from 1 foot to 10 feet away. At 10 feet away, it's going to be 20 dB quieter. Go from 1 foot to 2 foot, it'll be 6 dB quieter. Go from 1 foot to 4 feet, it's 12 dB quieter. Yeah? And therefore, you can actually calculate this using that same formula, 20 times the log of one distance divided by another distance. It's just the distance you started out with divided by the distance you ended up at. And you will get the dB difference in pressure. Okay? And this is something that you will run into all the time doing sound. It gets quieter the farther away you get from it. and you know this. I mean, you've lived this in your life. You've just never really understood that it can be predicted. So it can be predicted. It's actually very predictable. And those of you that were in the sound system engineering class last semester, we measured this across the soccer field. You remember? We tested this inverse square law, and we measured sound pressure at doubling of distances, and we were getting about a 6 dB difference, right? So it works. We proved it.
Until we broke it with line arrays.
Until we broke it with line arrays, yes. Okay, so let's do some inverse square law math. So you have this loudspeaker, and it's measuring 100 decibels worth of sound pressure at 3 feet away. How loud or how many decibels of sound pressure will it be at 30 feet away? You should be able to do this one in your head. Anybody want to take a crack at that without the calculator? Hmm?
80 decibels?
No. Way less than that. Oh, yeah. Sorry, yes, you're sorry.
80
Yes,
watts.
it's a 20 decibel difference,
Gotcha.
but it will be 80 decibels in the end. Yes, you're right. Sorry, I was misinterpreting what you were saying.
Right.
Okay, so why is it 80? Well, because 30 is just 3 times 10, right? And when you multiply the distance by 10, you drop 20 dB. So 80 decibels. See? You just did a logarithm in your head. You thought I was kidding a few weeks ago when I said we're going to be doing logarithms in our head in February. And you were all like, what? And like, you just did it.
Doesn't feel like it.
Yeah.
If only we hadn't been snowed out, I could have used this the other day.
There you go.
Because I was in the lab and I was listening to all the race cars go around, and I'm like, it's really loud. That's really far away. I bet if I went outside and measured how loud it is, and then used inverse square law, I could figure out how loud they are at the racetrack.
You could.
'Cause they were still pretty loud.
Yeah. Okay. So going back to this concept of loudspeaker sensitivity, so you look up the specs for a loudspeaker you have, and it says, hey, this thing generates 113 decibels worth of sound pressure at 1 watt, 1 meter, meaning you put 1 watt of power into it, you will measure 113 decibels worth of pressure at 1 meter away. How loud will it be with 1 watt at 30 meters away? This is another one. Well, let's try it. So we're basically talking about, the first thing that we want to know is how much decibels will we lose by going 30 meters away? So this would be 20 times the log of 1 divided by 30. So 1 divided by 30, log 10 times 20. I got minus 29.54 dB. Is that what you guys got? Okay. So I have 113 decibels at 1 meter, which means at 30 meters I would have 113 minus 29.54. Right? So what is 113 minus 29.54? Oops, 29.54. I got 83.46 decibels worth of sound pressure. Yeah? Questions? Pretty good? Okay. So here's the real thing. EAW actually makes this. Actually, I don't think they make this one anymore, but they used to. EAW used to make this loudspeaker called the JF100E, and its sensitivity was 97 decibels of sound pressure level, 1 watt, 1 meter. How powerful will your amplifier need to be to get 100 decibels worth of sound pressure at 10 meters? Okay, here's a real deal question. Someone would pay you money to figure this out someday. Okay? People have paid me money to figure this kind of thing out before. So, okay, let's figure it out. So ultimately, I want to know 100 decibels of sound pressure at 10 meters. Well, if I'm making 100 decibels at 10 meters, how loud am I at 1 meter?
10?
I don't know. I got to figure that out, right? So, because I know what the loudspeaker can do at 1 meter with 1 watt. The manufacturer told me. So, if I'm trying to get 100 decibels at 10 meters, I need to know how much am I making at 1 meter in order to do that, because I'm going to lose sound traveling that 10 meters. Yeah? So, how much am I going to lose going 10 meters from 1 meter to 10 meters? Yeah, that's a factor of 10, right? And what happens with force decibels when you go by 10? Yeah, 20 dB, right? So I'm going to lose 20 dB going that 10 meters, which means if I'm getting 100 decibels at 10 meters, that means I'm getting 97 plus 20 at 1 meter. Okay, so what's 97 plus 20?
117.
117 decibels at 1 meter. Okay. Well, I already know how to make 97 of those, don't I? It only takes 1 watt of power to get 97. So let me subtract the 97 from that, because I already know how to do that. I just want to know how many more dB do I need. So 117 minus the 97 is what?
We're just subtracting
Yeah.
what you just said.
Yep, exactly. So just making sure we're all following along here. Even I got.
Just the stare after 20.
It's like, is that right? Yes, that's right.
Well,
So,
look above.
yeah. I'm with you.
I wasn't confused, and now I am.
Yeah. Okay, so 20 more dB. Well, how do I get 20 dB? Using power. Because I want to add power to this loudspeaker and get 20 more dB. That's the ultimate question here I'm looking for. How powerful does my amplifier need to be? So let's find the power ratio for 20 dB. That would be 10 to the power of 20 divided by 10.
So 100.
So 20 divided by 10 is 2. 10 to the power of x is 100.
I did that in my head, Jason.
Nice.
No calculator.
Good job. Good job. Okay, so that's the power ratio for 20 dB, which means you multiply that number by any power level and you will get a power level that's 20 dB more. So what was the power level we started with? 1 watt, right? So times 1 is 100 watts. So for this particular loudspeaker, you put 100 watts into it, and you could end up with 100 decibels at 10 meters.
Well, you know.
Yeah, I mean, assuming there aren't any other variables that we haven't accounted for, right?
I'm not sure I get it.
Well, oh, sorry. I thought there was more, but there's not.
I just don't understand, like the 97 and then the 100 and how we got 100 watts and then adding 20 and subtracting 97.
Yeah. So basically, we're trying. What I'm trying to do here is merge these two concepts, because all of this is connected. So you put a certain amount of power into this loudspeaker, and it generates a measurable decibel output in the air.
Which is 97.
Yes. Put 1 watt of power into it, you get 97 decibels worth of pressure in the air at 1 meter away. But then what happens when you get farther away from that loudspeaker? You're losing pressure, right? So it gets quieter. My design criteria, I'm designing a sound system here, and I have audience people sitting 10 meters away from this loudspeaker, and I need them to hear 100 decibels worth of loudness.
Not the 97.
Not the 97. But the thing is, at 97 decibels, and I go 10 meters away, how loud will it be if I only have the 1 watt of power? How loud will it be in the audience? Yeah, it'll be 20 dB less than that, right? That's a long way away from the 100 that I want. Okay? So the question is, well, I'm only pumping 1 watt of power into the loudspeaker. What if I put more power into it? How much more power do I got to put in that loudspeaker in order to get the amount of sound I need at the audience? So, well, in order to get the amount of sound I need at the audience, which is 100 decibels at 10 meters, I'm going to have to generate more than 100 decibels worth of sound at 1 meter away, right? Because I have to count on losing 20 dB going through the air. So I have to make a lot more sound right next to the loudspeaker than I need in order to have enough left over by the time it goes through the air and gets to the ears. Okay? So I've got to generate 117 decibels right next to the loudspeaker in order to have 100 left. I think we did this
I
wrong,
was
actually.
following, but now I'm confused.
I think we did this wrong,
I think we
actually.
did too.
Now that this is why I was confused actually earlier. Let's do this again.
Great idea.
Let's do this again, because now I'm realizing I think we did it wrong.
I think we did too.
We got halfway through, and this is why I gave you that. This is why I gave you that weird look
When you asked.
about halfway through, and I was like, that number doesn't sound like it makes sense. My spidey sense was going off.
The only
And-
reason we were confused is
Yes.
because you told us to.
No, I know. I think I told you wrong. We're going to do this again. Okay, so 100 decibels at 10 meters. I am going to lose 20 decibels making that trip, aren't I?
Yes.
Which means I need to make how much at 1 meter? 120, right? This is the mistake we made before. So I'm looking for 120 dB at 1 meter. This is the mistake we made. Okay?
Okay.
So 120 dB at 1 meter,
Oh, so we're off it.
we know how to make 97 of that, don't we?
Yeah.
So minus 97, let's just subtract that for now.
Okay.
And what do we end up with?
73? No.
That's, 23.
23. So I have to figure out how to make 23 more dB. Yeah? So what's the power ratio of 23 dB? Because I'm thinking, what if I put more power into the loudspeaker? Well, what's 23 dB more power, right? So this would be 10 to the power of 23 divided by 10. Yeah? So 23 divided by 10. 10 to the x. Oh, this is making more sense now. So I got 199.52. Okay?
53. Actually.
53, yes. Thank you. Thank you. So, all right, then I multiply that by the 1 watt that I was using to get the 97, right? Because I already had that. So times 1, and I get 199.53 watts. So if I put 199.53 watts, otherwise known as 200 watts, I put 200 watts into this loudspeaker, I will generate enough sound pressure to have 100 dB left over at 10 meters away.
And Lord having our some people in the front row.
Yeah, that's pretty loud.
Okay, this makes more sense.
Yeah. I'm glad you asked because
I'm glad I asked too,
Yes.
because that was not right.
I was off for a minute there, and I was like,
No.
this doesn't feel right. And then I kept going for some reason, but I shouldn't have. I should have stopped
Only
him.
in the minus 20, that was like,
Yeah.
feels like some unnecessary steps.
Yep.
Like I feel like people
You were
know
right.
the answer
You were right.
in the 20.
You were right.
But thanks for going back,
Yep.
because this is helpful.
Okay. All right. How we doing? We good? Well, look at that. It's almost 3 o'clock right now. So when we see each other again on Tuesday,
It sounded kind of ominous.
weather permitting, I'm going to contradict something that I just said.
We are going to add 20.
Like the opposite of the inversion?
No, well, I said something about 15 minutes ago that I'm going to contradict on Tuesday. The thing I said 15 minutes ago was that decibels cannot be used to indicate an actual value. They only are used to show a relative value.
Bro, I wrote that down and put it in a box. Should I like cross it out?
No, it is true.
Okay.
That statement is true.
Just like stereo isn't real.
Yes. However, we are going to learn on Tuesday how you can, if we can all get on the same page about a couple of assumptions, then we can use decibels to indicate actual values. But it requires us all to agree about something.
Oh, is that like the weighting?
No.
Say
So,
more. I'm so curious.
On Tuesday, I will say more. Okay? So that's just a little tease for next.
You love a dramatic pause.
Yes.
Guys, do we think we'll have a meeting on Monday?